Today we are going to look at two more tests and the last two in our grouping of infinite series. So we're going to look at the ratio and the root test. And the ratio test is a great test to use on series that have factorials or exponentials. Is a great place to use the ratio test. So series that converge very quickly would be a good place to use the ratio test. And here's what the ratio test says. It says that if we have a series of non-zero terms, that the series will converge absolutely if the limit as n approaches infinity of the absolute value of any term and the term before it, or any term and the term after it, if you want to go backwards the other way. So a sub n would be any term, and the term after it would be a sub n plus 1. If that value is less than 1, then that series converges absolutely. But if that series is greater than 1, when I take the limit as n approaches infinity of a sub n plus 1 over a sub n, and if that's greater than 1, then it diverges. But the test is what we call inconclusive if we show that it equals 1. What that means is that we just need to use a different test. The ratio test wasn't the right test. It doesn't mean it doesn't converge or doesn't diverge. It just means we need to do something else to figure it out. So let's look at some examples. So the first example that we have is the sum from n equals 1 to infinity of 2 to the n over n factorial. Now this is a great series to do this with just because of the factorial and the exponential. Now we can't use geometric, even though 2 to the n kind of looks like it fits that pattern. The n factorial certainly does not. Okay, so what we're going to do first, before I go into my limit, I am going to go ahead and take the absolute value of a sub n plus 1 divided by a sub n, and my goal is to show its relationship to 1. All right, so here's what this looks like. Now I'm going to write it out the longhand way this time, and then in the future I'm probably going to skip this initial step. So my first step would be to say that this is 2 raised to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial. And my job right now is to show, doesn't look like a factorial, my job is to show its relationship to 1. Now, I want you to use your properties of exponents with me for just a moment. And if we look at just this 2 to the n plus 1, do you agree that I can rewrite this as 2 to the n times 2 to the first? If we undo our properties of exponents, I can write it that way. Now let's also think about the factorial. If I have n plus 1 factorial, what does that mean? Well, it means that I have n plus 1 times n minus 1 times n minus 2 times n minus 3 times n minus 4, all the way down until I get to 0. And so I could rewrite this n plus 1 factorial, as n plus 1 times n factorial. Why? Well, because n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down to 0. So I can rewrite this factorial in this form. Now I'm going to multiply it by the reciprocal of that denominator. And this would be the absolute value of all that. And really, this is going to be the step I probably am going to take the first every time. I'm probably just going to write it as, in the ratio test, I'm probably just going to write it as 2 multiplied fractions, just because it looks easier to see, or it's easier to see. And now I can cancel out like terms. So I have 2 to the n over 2 to the n. I have n factorial over n factorial. Here's what this means. The actual problem that I'm going to work with is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, which we just simplified to be 2, over n plus 1. And my job is to show its relationship to 1. And if I take the limit of this, the limit as n approaches infinity of 2 over n plus 1, this will make a great big huge number in the denominator, so I have 2 over a huge number, which means that this value is getting closer and closer to 0. And 0 is less than 1, and therefore this converges. And usually we would say why. I already know I'm using the ratio test, but we're just going to say it anyway. By the ratio test. Okay, let's look at the next one. Or hit pause. Try the next one on your own. See what you think. All right, maybe you had a chance at it. What we're going to do first is we're going to take a sub n plus 1 over a sub n. And the way I'm going to write that is as two fractions being multiplied. So I would have n plus 1, so n plus 2 factorial over 3 to the n plus 1 times 3 to the n over n plus 1 factorial. And now I'm going to rewrite this again. N plus 2 factorial would be n plus 2 times n plus 1 factorial over 3 to the n times 3 to the first. And I'm going to multiply that by 3 to the n over n plus 1 factorial. And now I can cancel out my like terms. So the problem I'm actually going to solve is the limit as n approaches infinity of n plus 2 over 3. And if I take that limit, what I get is infinity. And the problem with that is infinity is greater than 1. Therefore, this diverges based on the ratio test. So this diverges by the ratio test. Now, we could have used the nth term definition on this. You guys, there are multiple ways that we can solve these. And so I could have used the nth term, and this is what that looks like. If I had just taken the limit, the nth term only proves divergence. So if I take the limit as n approaches infinity of n plus 1 over 3 to the n, I get infinity. Factorials dominate exponentials, and therefore this is not equal to 0, which is the rule for the nth term, so this diverges by the nth term. You do not need to say all of them. Just pick one that makes the most sense to you. Okay, let's look at what it looks like for the ratio test when it's inconclusive. Here we go. We're going to do a sub n plus 1 over a sub n. And I am going to, so I have n plus 1 over the cube root of n plus 1 times the cube root of n over n. Now, the bummer part here is there's really not a whole lot of simplification. So the problem that I'm going to be solving now is the limit as n approaches infinity of n plus 1 times the cube root of n over the cube root of n plus 1 times n. Now I want you to think about limits to infinity. One of the rules that we have is that if we can look at the n behavior of the function, what we used to call the horizontal asymptote way back in Algebra 2 trig, if we can look at the n behavior of this function, what happens as we go on forever, we can do that by looking at the degrees of the numerator and the denominator, as well as their leading coefficients. And what that's going to tell me is my limit to infinity. So let's think about what this might look like. If I were to be able to FOIL things out and simplify them, really what this problem would be saying, or the n behavior we'd be focusing on, is I would have n to the 4/3. That's n times the cube root of n. And in the denominator, I would have over n to the 4/3 as well. This is my n behavior of the function. And that limit would be 0. Therefore, this would be inconclusive using the ratio test. Meaning we just did all that work and all that thinking for nothing. We don't know if it converges and we don't know if it diverges. Now, we could use the nth term test on this one. Let's think about why that might be better. If I had the limit as n goes to infinity, and I rewrite this problem as n over n to the 1/3, which would be the limit as n approaches infinity of n to the 2/3 power. I know this diverges by the nth term test, meaning if I substitute in infinity or deal with plugging in infinity or thinking about that limit to infinity, my limit is infinity, and that's not equal to 0. So we could say this diverges, diverges, only has one s, by the nth term. Let's look at another test. I think what you're going to see is that the root test looks pretty darn similar to the ratio test, at least in its conditions. And the root test for convergence or divergence works really well in series that have powers, nth powers specifically. What's important to note is that the root test is always going to be inconclusive for p series, so we don't want to use it for that. We really want to use it when we have an nth power. Now keep in mind, sometimes other tests may be easier, but I want to show you how this root test works. So it says that if we have any series, the series will converge absolutely if the limit as n approaches infinity of the nth root of the absolute value of the a sub n is less than 1. And then it diverges if the limit as n approaches infinity of the nth root of a sub n is greater than 1 or is infinity, which is kind of silly because those really say the same thing. And the root test is inconclusive if that limit equals 1. So let's look at an example. If we look at this first example that we have the series from n equals 1 to infinity of e to the n over n to the n. Now, I want you to pause for a moment and think about whether this might be geometric or not. It's not. The reason this isn't geometric, remember our geometric series, we would need to be able to write, so this would be e over n to the n power. So it looks really close to geometric, but the problem is this is not a constant ratio, and therefore it's not geometric. Okay, so now that we have that out of the way, let's look at the nth or the root test. And if we deal with the root test, again, I'm going to do this a little bit similar to the last one in that I'm going to just take the nth root of my a sub n, my explicit definition here. And so I would have the nth root of, and maybe it would help you to look at it how we wrote it just to see if it's geometric, like this. And if I take the nth root of e to the n over n to the n, or if I take the nth root of e over n to the n power, I know this simplifies to e over n. So really the problem I'm solving is the limit as n approaches infinity of this e over n. And e is a constant, and when I divide that constant by 0, divide that constant by infinity, I get 0, which we know is less than 1, and therefore this converges by the root test. Okay, normally I would have you pause and try this next one, but I do want to look at this next one together because it's a little bit messy. This one fits the pattern of what we did before with the ratio test, and in fact I'm going to show you that I think the ratio test might be better for this, but that we can still use the root test. So the root test says that I'm going to go ahead and take the square root, or the nth root of n cubed over 3 to the n. And what that leaves me with is n to the 3 over n, because I don't know the nth root of that, over 3. Okay, so the problem I'm actually solving is the limit as n approaches infinity of n to the 3 over n over 3, which we could probably rewrite and make our life a little bit easier and say the 1/3 times the limit as n approaches infinity of n to the 3 over n. Let's think about this expression. If I were to think about what the limit is as n goes to infinity, what you should be thinking is that this would be infinity raised to the 0 power. The problem with that, that's one of our indeterminate forms. The bigger problem with that is that we now need to change this to a form that we can use L'Hopital's with. So what that might look like, so I'm going to focus on just this part for a moment. And what I'm going to need to do, because I have an nth power, is I am going to take the natural log of this. So the limit as n approaches infinity of the natural log of n raised to the 3 over n, which equals the limit as n goes to infinity of 3 over n times the natural log of n. And I am writing it this way for a reason, only because when I get it to this form, thinking about infinity here, I would have infinity in the numerator over infinity in the denominator, meaning it is now L'Hopital ready. So I'm going to use L'Hopital's. So I would be doing the limit as n approaches infinity of 3 over n over 1. And that limit is 0. Now remember, I need to exponentiate that. So what this looks like up here is I have 1/3 times e raised to the 0 power, and that 0 comes from right here. So 1/3 times e to the 0, and 1/3 times e to the 0 is 1/3 times 1, which is just 1/3. And since 1/3 is less than 1, because remember my whole goal is to compare this to 1, we know this converges by the root test. Now, this problem may have been better using a ratio test. So I'm going to zoom out and we're going to look at just what that might look like. Whoops. If I use the ratio test, and I'm going to put this right here. Let's see if I can fit it right there. I would be taking the limit as n approaches infinity, and the ratio test would look like this. N plus 1 to the 3rd over 3 to the n plus 1 times 3 to the n over over n to the 3rd, which would be the limit as n approaches infinity of n plus 1 to the 3rd over 3n to the 3rd. And I'll leave that for you to verify. And if we do this, notice my n behaviors are the same. It's both to the 3rd power. If I were to FOIL this craziness out, we'd have n cubed plus 3n squared plus 3n plus 1. And so both my leading coefficients, my degrees would be 3, and my leading coefficients in this case would be 1 over 3. So this would equal 1 over 3, which is less than 1, which converges then by the ratio test. So you can see we can often use multiple rules. Sometimes some are easier than others. So what I want you to do is hit pause and try this last example. Hopefully you had a chance to give it a go. And I'm going to use the root test. So I'm going to take the nth root of n over 1 plus n cubed to the n power. This gives me n over 1 plus n cubed. So the problem I'm actually doing is the limit as n approaches infinity of n over 1 plus n cubed. And we know that it grows significantly faster in the denominator. So therefore this would be 0, which is less than 1. So this converges by the root test. And there you go, the ratio and the root test.